Okay, so the next thing we have to talk about with particle kinematics is circular and spherical motion. And to talk about these, we need to use two more variables, two more quantities, the angular velocity and the angular acceleration. And so the angular velocity, omega, it's a vector. And you can think of, so any vector you can think of as a direction and a magnitude. So this has a magnitude that's defined by the rate of change with time of the angular position that's swept out by an object as it goes through. So like if an object's moving through a circular path, if this is the object and it goes from here to here along the path, then this is the angle that I'm talking about. So it's d theta dt, and its direction is the axis it rotates about. You can think of it as like the hinge that this, if you think of an object moving in a circle as being like on a string or something moving around a, a pencil, or on a beam that's rotating about a hinge, then its direction is the axis of that hinge. Okay, so if this object is moving this way around this circle, then we know that the direction of its angular velocity is either coming out of the page or into the page, right? Either of those are an axis of that rotation. So how do we determine which one of those two directions? Because a vector can only be, yeah, right. So right-hand rule. So determined by the right-hand rule, or following the right-hand rule, let's say. A couple of things to notice about this. Is for this to work, first, your angular position has to be in radians. That means that the angular velocity has units, or SI units at least, of radians per second. It's always going to be radians per whatever unit of time you're using. Third, any circular or spherical motion has an instantaneous angular velocity vector. And fourth, this is maybe the first case in this class where we see an important difference between what happens in 2D and 3D. So angular velocity is easy to define in 2D. So the angular velocity is just equal to d theta dt. Following the right-hand rule, it's easy to use that in a calculation. In 3D, that definition still holds, but doing the calculations gets really complicated. And so in our problems, usually angular velocity is just going to be something that's given to you when we do three-dimensional problems. To actually go from how the angular position is changing to calculate the angular velocity is really hard. And it has to do with the fact, because you ask, it has to do with the fact that, like, say you have a sphere and you have reference positions, you know, like you have a coordinate system, and say an object's over here. How do you define its angular position in terms of like a rotation about x, a rotation about y, a rotation about z, you know? Like once you do the rotation about the first axis, it becomes like doing a second rotation about another axis. There's an indeterminacy problem because if you rotate to a certain position, a rotation about another axis doesn't move it anywhere. And so you can do some things, right? Like if you rotate over to rotate all the way over to one of the other axes, now rotate about that axis, the thing doesn't move, you know? So you're sort of locked in place there. And there are ways around that where you do rotations about axes that change as you rotate. So you actually like rotate the coordinate system with you, and now you can rotate about this one. But it gets hard. That's enough. So yeah, that's why when we're doing problems with circular motion, where something's moving in a plane, you can be given the angular position as a function of time, and you can actually calculate that angular velocity. But in three-dimensional problems, the angular velocity is just going to be something that you're given as a function or as a value or whatever. It's hard to calculate it. So it's hard to calculate from position information in 3D. Okay, so here's a two-dimensional example. So let's say that in 2D, an object's position is given by the function 10 cosine 2t, 10 sine of 2t. Okay, so that motion looks like this. It's a circle with a radius of 10. So what is the angular position as a function of time? Well, if it's, you can see that this is just a simple, like, whatever is inside here, inside the cosine and inside the sine, just gives you the counterclockwise angular position from the x-axis, right? So you can see that theta as a function of time is just equal to 2t. And so now if you wanted to calculate the angular position, the angular velocity as a function of time, then omega is just equal to d theta dt. It's just equal to 2, whatever the units are, radians per second squared. Yeah, well, it's tracing out this path, and if you're trying to figure out, like, so at some point, say it's going to be over here with an angle theta from the positive x-axis. It's going to be over there when the argument inside cosine and sine is equal to whatever this theta is, 120 degrees. That's just, so like if you think of the unit circle, right? That this function tells you which point on the unit circle you're at based on the angle between the positive x-axis and whatever theta is. And that's the same thing that's happening here. It's just that instead of theta, we have 2t. That's just what a function like this, I mean, you can think of pull out the tens. And you have 10 times a unit circle where the angle that you're sitting at is determined by the function 2t. Yeah, sorry. Okay, so now let's go to angular acceleration. Once you've defined the angular velocity, angular acceleration is easy. It's just a time derivative. So the angular acceleration is also a vector, and it's equal to omega dot, the time derivative of the angular velocity. A couple of things to keep in mind about angular acceleration. For circular motion, so for circular motion in a plane, the angular velocity vector and the angular acceleration vector are always parallel. So let's say they're always parallel to each other. And they're perpendicular to the plane. They point right out of the plane, perpendicular to the plane of motion. Also, if you're talking about circular motion instead of spherical motion, if the angular velocity and the angular acceleration have the same sign, then the circular motion is speeding up. if they have opposite signs, then it's slowing down. Okay, so let's say, as an example, that you have circular motion that's defined by the angular position function theta is equal to -5t squared.
They were opposite signs. It would eventually come to a stop.
That's right, and then it would start, well, it would come to a stop, and then it would start moving the other direction, which would switch the signs of the angular velocity, and then it would be speeding up. All right, so say you have this circular motion. Is it speeding up or slowing down? Well, one way to figure that out is to calculate the angular velocity. That's equal to -10t. So that, that's just equal to theta dot. And now the angular acceleration is -10. That's omega dot. So for any positive time, which is all we're going to deal with, it seems a little arbitrary, doesn't it? But that's just how everyone does it. That's what we're going to do too. No negative times. So for any positive time, omega and alpha have the same sign. So this is speeding up. Any questions about that? Okay, so now one of the useful things about omega and alpha is that we have a nice simple relationship between translational velocity and acceleration and rotational or angular velocity and acceleration. So let R be the vector from the center of rotation to the particle. R is a vector. Then the velocity of that vector, this is the translational velocity, is equal to the angular velocity crossed with the R vector. And the acceleration of that particle is equal to the angular acceleration crossed with R plus the angular velocity crossed with the quantity angular velocity cross r. For the acceleration expression, this first term, alpha cross r, is the no, that's the tangential acceleration. That's the one related to speeding up and slowing down. And this one, omega cross r, is the centripetal acceleration. And that's the one that you can think of as defining the circular or spherical motion, or maintaining the circular or spherical motion. Okay, so for example, if you have a particle that's moving in circular motion, so moving in a circular path, and the angular velocity vector is equal to 0, 0, negative 2t squared. And at the time 2.5 seconds, the particle is in this position. So the circle has a radius of 5 meters, and at time equals 2.5 seconds, this is the particle. And we want to know what are the particle's velocity vector and the particle's acceleration vector. And you can see, like, when we get into kinetics, what the point would be of trying to figure this out. So say you're given this particle's motion in terms of this angular velocity vector, and you're trying to figure out the forces acting on it, you know its mass. The only relationship that we're going to have between its motion and the forces on it is Newton's second law, which deals with the acceleration. So we need to be able to go from this angular velocity to the acceleration so we could use Newton's second law. Okay, so part A. We know that the velocity vector is equal to omega cross r. The omega vector, we know that it's at time equals 2.5 seconds, so that is 0, 0, negative 12.5 if you plug 2.5 seconds into this function. And at this location, what's the r vector? Yeah, and I guess I didn't give a coordinate system, but so 0, 5, 0. So take that cross product, and you get the vector 62.5 meters per second, 0, 0. Does it make sense thinking about physically what's going on that that this would be in the positive x direction? Yeah, because we know that the angular velocity is clockwise. We know it's rotating clockwise. And so up here, it's like this. We know the velocity is going to be tangent. So that makes sense. And then for part B, the acceleration is alpha cross r plus omega cross r I had something like this before. You're going to see this equation all the time. So remember, this is, I'll use this one. All ripe watermelons will rot. That's a good one for this summer. Okay, so all ripe watermelons will rot. Never forget it. I mean, you can forget that fact about watermelons, but don't forget this formula. Okay, so how do we come up with the angular acceleration? Yeah, that's right. Take the derivative of this, so it's going to be 0, 0, negative 4t. And then plug in 2.5 seconds for 4. And so you get 0, 0, negative 10. That's evaluating this at time equals 2.5 seconds. And so the acceleration is 0, 0, negative 10 crossed with 0, 5, 0 plus 0, 0, negative 12.5 crossed with 0, 0, negative 12.5 crossed with 0, 5, 0. What's the deal with the associative law and cross product? Does it matter what we multiply first? It'll come out the same either way. You have to follow the order, that's right. But not the but you can group it either way. Yep. So if you do that, you get 50 meters per second squared, negative 78.125 meters per second squared, 0. So think about that motion, and do the directions of those, the components make sense? Question?
So does it matter if the C of phi y direction?
Mm-hmm.
Does it matter what you say the phi in the x direction? Is it just your radius, the radius vector? So couldn't you put it either in the x or the y?
Well, it depends on where the particle actually is and what the coordinate system is. So yeah, this is
What is the vector cross
0.
Do we even need to do that?
Oh yeah,
I mean,
I told you. Yeah, I'm glad you thought of that, because yeah, you do have to group those a certain way. So yeah, it's not associative. Okay, so you do have to do it like this, because otherwise it would always be 0. Yeah. I'm going to edit that out of the video. I did it right earlier, and then I thought it didn't have to be there, but it does have to be there. It is, if it's always 0, it's way easier. It just isn't right. Yeah, that's the downside. Everything's a trade-off, you know. So yes, you have to do these two together first, and then do that last cross product last. So does the direction of this acceleration vector make sense? Okay, so we know that it's moving in the moving in the clockwise direction. We know it's speeding up. Because of where the particle is in the circular motion, the centripetal acceleration needs to be in the negative y direction, and we have that. And since it's speeding up, the acceleration has to be in the same direction as the velocity vector, and we have that too. So that makes sense, roughly. Okay, what about, so this goes nicely with the relative motion equations. So the relative motion equations say that if you calculate the position, velocity, and acceleration relative to one object, let's call it A, and you want the position, velocity, and acceleration relative to another object, B, you can figure those out as the position of the object you want relative to B is equal to the position of the object relative to A plus the position of A relative to B. Okay, so if we're talking about, so if this is A, this is B, and this is the moving object, O, okay, then you can figure out the position of, so say that you're on A with a video camera, okay, and you're measuring these properties of O, of this object, relative to where you're standing. And you also are measuring the position, velocity, and acceleration of this other place, B, relative to where you are with your video camera. Then you can use this calculation to figure out what position, velocity, and acceleration someone standing at B would measure. Okay, so the velocity and acceleration equations look similar. The velocity vector of O relative to B is equal to the velocity of O relative to A plus the velocity vector of A relative to B. And acceleration, O relative to B is equal to O relative to A plus A, sorry, those should be accelerations. A relative to B. The way to remember these, by the way, is to think of like fraction multiplication of subscripts. You know, that's not like a real thing, but it's just a mnemonic device. So, like, notice if you multiplied the fractions O over A times A over B, the A's would cancel and you'd get O over B, and that's what we want. Okay. So, the way this works, so let's do an example. No, let's do an example next time. So what I'm going to do next time, I'll start with this, is let's say that there's this like super version of a Ferris wheel where this arm rotates like this, and this arm rotates like this, and you want to figure out what the velocity is of somebody on this doing that sort of compound rotation. Well, the way we're going to do that is we're going to figure out what the velocity and acceleration are of this point, and then we're going to use those relative motion equations. Once we figure out, you know, then we're going to sort of pretend that this is fixed, use the circular motion equations to calculate the velocity and acceleration at this point relative to this, and then add those two motions together to get the total. Okay.